All right. Sorry, my wife couldn't find her keys, and still can't, but I didn't ever touch them, so I'm clear. Anyway, hopefully you've had a chance to take a look at these. Noticing that e to the x grows faster, we should get 0. Okay. So when the denominator of the fraction grows faster, the limit is 0. And if you use L'Hopital's rule, you can find that that's 0 anyway. And then over here, you should have gotten that that was infinity, because x is approaching infinity. E to the x grows faster. X grows faster than ln of x, and so this one is infinity as well. Okay. And so really, that's really about it as far as the concept goes. So I'm going to give you guys a couple challenging problems, though. I know you're probably thinking, oh, how does this get any harder? Well, as it normally does. Let's see how it goes. Again, keep in mind the bubble theorem, and let's see how you do with these problems. Let me go ahead and write this one down. I'm going to start you off with this one and let you chew on that one for a while. Limit as x approaches infinity of e to the x over x factorial. That's going to come up in some later sections, but it would be worth mentioning right now because it'll be, in fact, I'm not going to give you the answer to that one yet. So you're either thinking it's either infinity or it's going to be 0. And I'll let you decide about that. But I will show you how to do these other ones, and I'd like you to pause the video after you see what the problems are. E to the x plus e to the negative x over 2 all over e to the x. Okay, so I'll go ahead and show you the solution to that one right now, so pause the video if you don't want to see it. What would I do here? Limit as x approaches infinity. I'm going to bring this 1/2 out in front, and I'm going to write it as e to the x plus e to the negative x, and then multiply by 1 over e to the x. Okay, or I could divide by e to the x. Nevertheless, I've got 1/2 times, and if I divide each of these, if I distribute this e to the x to both terms, okay, then it's got an e to the x there and e to the x there, and what I end up getting here is 1 plus e to the negative x over e to the x. Okay, and then we're getting there. 1/2 times 1 plus, now this here, e to the negative x up top is going to be e to the x down below, and so that's going to be e to the 2x down below, right? And then, so therefore, when x goes to infinity, this term right here is going to go to 0 because the denominator is increasing rapidly, and we've got a constant in the numerator, and so we just get 1/2 times 1, or just 1/2. And so hopefully you were successful at that one. Okay, I'll show you a couple other tricky ones. Again, we're going to save that one for class. A couple tricky ones would be like this. Limit as x approaches infinity of 4 to the x over e to the x. Okay, so pause if you don't want to see the solution. It's kind of a concept one. You should remember that a to the x over b to the x is equal to a over b to the x. So we can rewrite this as the limit as x approaches infinity of 4 over e raised to the x power. Okay, now if you think about 4 and you think about e, you know that 4 is a number greater than e being 2.718. So this number right here, this is the concept, okay? You don't, by the way, have to show any work when you're ever finding a limit. When you understand the concept of when x gets really, really big and relative growth rates, limits are actually pretty easy to find. So here's a big concept, though. This number here is greater than 1. Okay, think about a number greater than 1 being raised to a power that's getting really, really big, big beyond bound. So as long as that number right there is greater than 1, the limit is infinity. If that number is equal to 1, 1 to the infinity is 1. If the number is less than 1, then we have a different story, but we have 0. So 1 is the kind of like the dividing line. If that number is 1, then if it's 1 being raised to the infinity, well, or greater than 1 raised to the infinity, then it's going to be infinity. It's going to grow beyond bound. You could draw the graph of that function. It's going to grow pretty slowly at first, but again, when x gets really, really big, the value of that function is going to get really, really big as well. Okay, so you might want to pause and rewind that one. Kind of a tricky one. And likewise, the limit as x approaches infinity of e to the x over 4 to the x. Well, I'll let you think about that for a second. Using the same reasoning here, we're going to get a limit of 0, okay, because the denominator is going to grow faster than the numerator. Okay. A couple other tricky ones. If we take the limit as x approaches infinity of, let's say, the square root of x to the 4th plus 5x over x squared. Okay. Well, if you remember back from chapter 2, we said, look, when x is getting really, really big, there's going to be one term in the numerator that's going to dominate that numerator, and the one term in the numerator is going to dominate is going to be this x to the 4th. It's still under the radical, yes, but this 5x is going to be insignificant. We can act as if it's not there, okay? Because when x gets really, really big, again, 5 times x is going to be insignificant compared to x to the 4th. And so really, what we have here is the limit as x approaches infinity of the square root of x to the 4th over x squared. Well, since 5x is insignificant, we can throw it out, and that's equal to the limit, then, as x approaches infinity of square root of x to the 4th is x squared, and x squared over x squared is just 1. So we have the limit of that kind of ugly looking function is just 1. Now this works, guys, when x is approaching positive or negative infinity because the x values are getting really, really big. Let me give you one to try on your own and see how it goes. Limit as x approaches infinity of the square root of 3x to the 6th minus 2x all over 5x to the 3rd. Okay, so pause the video if you don't want to see the solution, and I'll go ahead and do this. 2x, I'm going to throw that away. It's insignificant compared to the radical 3x to the 6th. But I'm going to rewrite that as radical 3 times radical x to the 6th, which is x to the 3rd, over 5x to the 3rd. And again, we have the limit as x goes to infinity. And so the x to the 3's cancel out, and we get radical 3 over 5. That's the limit. So limits can be fairly straightforward as long as you understand a few basic things. Relative growth rates, and we'll get back to you on this function right here. This is the big one. We'll talk about that in class. I'm curious to see what your answer is. Please tell me when you get to class, and I will see you then. That's it. No more work for you. See you in class. Well, actually, don't forget those. Don't forget the 2 FRQs that are due tomorrow, and then also the that online quiz that I had you guys do. So there's plenty of work to keep you busy. Have fun.